Okay, good morning everybody. So, let us continue with the discussion what we are having in the previous class. So, we are discussing the different balance law, angular momentum balance, linear momentum balance, right, and we have defined the Cauchy stress tensor, right, Cauchy stress, and then Cauchy stress tensor we have denoted as like sigma and tilde, right, and that is relating the traction vector at a plane with the unit normal vector of that plane by that relationship, and that follows the from linear momentum balance we see that this is linear momentum balance, right, and then from angular momentum balance we see that it must satisfy this one. So, these are the equilibrium equations, right, and then what we have defined that acceleration, there can be two different kind of reference frame with respect to which acceleration is defined. One is Lagrangian and another is Eulerian. Lagrangian is the description which is with respect to the reference or undeformed configuration, reference or undeformed configuration, undeformed configuration, that is Lagrangian description. Eulerian description, or it is also called updated Lagrangian, Eulerian or updated Lagrangian, updated Lagrangian. Updated Lagrangian is with respect to the deformed configuration, deformed configuration, that is what we have defined. So, basically we have a body, right, in we have a coordinate system x, y, z, right, and this body is deforming and going to a different configuration. This is a t is equal to 0, this is maybe t is equal to tau, this is tau is pseudo time. Okay. So, every point on P is being mapped to a point here. So, in undeformed configuration we denote everything by capital letter, whether in deformed configuration we denote everything by small letter, and so any line segment or any vector, if it has a d capital X bar, is also mapped to a line segment or vector segment d small x bar, right. So, when everything is denoted with respect to undeformed configuration, so this is undeformed, this is original or undeformed configuration, right, undeformed, and this is deformed, deformed configuration. So, when we consider with respect to deformed configuration, then it is Eulerian, right, and in Eulerian, so in Lagrangian what so there are two approach, Eulerian and Lagrangian, right. So, in Lagrangian what we do, we follow so you follow in Eulerian we follow spatial point, right, spatial point, and we follow material point, right, material point. So, we fix our position in space in Eulerian description, whether in Lagrangian description we follow each and individual material point and we try to study the motion. In Eulerian we try to study the motion by fixing the space, fixing the position points on space, and then we study the behavior of the solid as it behavior of the continuum as it flows to that. So, this is more convenient, Eulerian is more, or updated Lagrangian more convenient for fluid, although solid can also be described in this. Lagrangian is for solid, and the reason for that is that for solid the deformation everything is very much dependent on history dependent, right. That is what we always go back, we need to go back to the original or undeformed configuration and describe everything with respect to that. That is why Eulerian Lagrangian description is more suitable for solid, whereas for fluid we find that Eulerian description is more convenient, because we can fix our points on space, and then we study the behavior of the fluid particle as fluid particle as this is passing through that point. So, in doing so, the difference in acceleration comes. So, for Lagrangian this is, we can directly take the total derivative, right. If we define the velocity vector something like that, right, capital V, this is the Lagrangian description, this is Lagrangian, and then for Eulerian we have seen the acceleration is denoted by, because acceleration is denoted by dv dt, dv dt, this is the local acceleration, and then we have to differentiate dv small dx into dx dt, because it is fixed by in space, because we have here it is that we are following the material particle. So, we can directly take the derivative of the velocity vector or displacement, but here we have fixed a position in space, it is a function of x and t. That is what I have to take the first the derivative with respect to time, and then because we have fixed in time, so you have to take, you apply the chain rule, right. The velocity, the differentiation of the velocity with respect to the spatial point, and then of course, when passing to the axial point, right, that is also there is change in time involved, and that is what you see, that dv dt plus dv dx into v. So, this is of course vi, this is vi, and then this we are going to write j, okay, vi. So, then we can see this is vi dot plus gradient of velocity, I mean vi comma j, vj, or if we can write in, this is indicial notation, or if you want to write in vector notation, using vector notation, then u double dot is nothing but v dot v dot plus gradient of this velocity vector, and then dot product with respect to velocity like this, okay, this one, of course this is small, this one, these are all small v, please note that, please, small v, small v, small v, small v, small v, small v, okay. And do you see that this is nonlinear term, and this one is called local acceleration, and this is local acceleration, the time variation, and this is called convective acceleration, which is conventionally used in fluid mechanics in control volume. So, this part convective acceleration, this is always, I mean that we have, so then acceleration, when you see that this term, the convective one, convective v I comma j, v j, right, then we can, and then we get all three axes. So, we can see that this is non-linear, and that from the very beginning, based on the approach, because of non-linearity, fluid mechanics become complicated from the very beginning, and that is what we see, that is what turbulence or all the kinds happens, right. So, this is Eulerian description. Nevertheless, although we use Lagrangian traditionally for solid and Eulerian for fluid, but one of them can definitely be applied for for both, okay. So, that is not a problem, okay. So, after doing that, what do we try to do, that what we see that it is very important to see that with respect to which configuration we describe the motion, with respect to which deformed and undeformed. So, then for as far as infinitely small deformations are concerned, then deformed and undeformed we do not distinguish, okay. We do not distinguish between deformed configuration and undeformed configuration if it is infinitely small deformation. That is what we do not talk about even other stress measures, we just only see these are the more than enough, okay, for our conventional mechanics that we learn until now. For infinitely small deformation, we do not distinguish between deformed and undeformed configuration. However, if it is a finite deformation, then we have to distinguish between deformed and undeformed configuration, okay, for finite deformation, right. So, for finite deformation, we have to distinguish between deformed and undeformed configuration, right, deformed and undeformed configuration. We cannot, okay. However, for infinitely small, those are same, okay. So, deformed configuration maybe we will denote as gamma 0 and this is capital gamma, okay, and then the surface traction whatever we are writing, this is lambda 0, this is maybe capital lambda, that way we write, right. So, this is body, it is going to this, and then what we have defined that. So, then from the deformed and undeformed, what we have seen that traction vector and then Cauchy stress tensor. Cauchy stress tensor is always referred to the deformed configuration. So, Cauchy is always with respect to the deformed configuration, deformed configuration, that is the deformed, deformed. So, then when we see, if you can recall, Cauchy stress tensor, it is basically mapping between if they small d bar small dA, and then t bar. So, traction, so normal vector and the traction, so both are defined in the deformed configuration. So, t bar and n bar are in deformed configuration, in deformed configuration. Deformed configuration means capital omega, you understand that. So, when we define the Cauchy stress tensor, it is always with respect to deformed configuration, we see, and then we have seen that the small external. So, the internal forces can be related right, how internal forces can be related like n bar dA. So, these internal forces is in deformed. So, all this quantity, all these are in deformed configuration, in deformed configuration, right. All these are in respect to deformed configuration. So, Cauchy stress tensor is everything is in deformed. However, then we went back to our second year strength of material course, or engineering mechanics course, and what we have defined that we some during conducting this axial tensile test, right, I mean the standard tensile test, right, tensile test, what we have defined that, see we defined two measures, right. We traditionally when we test the specimen, if you can recall that this was for the nominal stress tensor, but this one was actual, we have plotted that, right. So, when we plotted this strain with stress, right, then we did not, when we consider the nominal one, that is whatever external axial. So, this was the specimen, if you can recall, standard steel specimen, right, and then we are applying forces P, that is changing, right. Of course, it is a displacement control environment, right, displacement control testing. So, then when P divided by or A, capital E is with respect to undeformed, always it is fixed, but this was P by A, and this A is a function of, it is always changing. So, that is what you see, this is the true stress, true, and this is the nominal stress, nominal, right. So, we can see really that the stress measure really are dependent on the reference configuration with respect to which it is being defined. So, Cauchy stress tensor that we have generalized here, that is nothing but true stress, you see it. So, sigma A is P by A, sigma A by E is P by A is the true area. So, that was the true tensor, and this is in 3-dimensional analogy, this is nothing but the Cauchy stress tensor, Cauchy, right, Cauchy stress tensor, stress tensor. So, similarly, can we have an analogy for the nominal? Yes, that is what we told, that the analogy is the first Piola-Kirchhoff stress tensor, Piola-Kirchhoff stress tensor. And what is first Piola-Kirchhoff stress tensor? So, now we will go back there. So, I mean here. So, here I will just write it down. So, here I am having the body, okay, and then here I am having a deformed body from here to here. This is undeformed configuration, this is deformed configuration, and undeformed or deformed must be a complex mapping. So, x bar must be a very complex mapping of like x bar. This is very nonlinear and complex, right, nonlinear mapping, nonlinear complex mapping, that we are yet to decide, right. That is what this mechanics course is about, right, complex mapping between these two configurations. This is deformed and undeformed configuration, right. Anyway, so this is the point P. So, then what this deformed configurations P. So, what we are saying then that we want to find out the internal forces, okay, internal forces at a point, right, internal forces, and then based on some so maybe dF bar. So, that internal forces in the deformed configuration dF bar, okay, is what? It is basically is nothing but then we are referring with respect to undeformed. This we are referring with respect to undeformed. Undeformed means n bar dA. We are considering a small area in the undeformed configuration, which is characterized by the unit normal to it, that is capital N bar, because capital N bar refers to undeformed configuration. And then we are relating the internal force in the deformed configuration, right, internal force in the deformed configuration to this. So, then the N bar dA, and that is what is the T bar, understand that T bar N bar T, dF is T bar N bar dA. Okay. So, this T bar is so P tilde N bar dA, P tilde. So, P tilde is nothing but it is nothing but nominal stress tensor, nominal stress, or it is also called first Piola-Kirchhoff stress tensor. P is Piola for and K is Kirchhoff, right, Piola-Kirchhoff stress tensor, first Piola-Kirchhoff stress tensor, right. So, do you so what you see that although the internal force that we are trying to find out, this is with respect to what? With respect to gamma, I mean capital omega, and this is with respect to capital omega 0. So, it is undeformed, but this one is with respect, that is why it is called a 2-point tensor, right, 2-point tensor, because if we call the Cauchy stress tensor, it is all with respect to undeformed, with respect to deformed. So, n bar was small n bar dA, right. So, that is why it was 1-point tensor, but here it is 2-point tensor, because it referred to both the configuration. One leg is in the deformed, whether the other leg is undeformed, that is why it is 2-point tensor, and then a separate subject is there which discuss with this is Lie algebra, okay, Lie algebra, Lie group. Okay. So, now once we have defined that, then let us consider the momentum linear momentum balance and then angular momentum balance, how they changes with respect, or whether they remain intact as we have seen in comparing these Cauchy stress tensor, what difference does it make. Okay. So, let us consider linear momentum balance, So, when we consider linear momentum balance, what we are going to consider, once again this is the body, and on that body this is omega, right, and then on the body we are considering, okay. So, this is deformed body, maybe this is deformed body, and then on this body I am just considering a point and a subdomain, I am separating out the subdomain. The subdomain I am just separating it out, okay. This subdomain I am separating out, and in this subdomain what are the forces that is acting? The forces that is acting is the inertia force, okay, minus rho u double dot, right, and then a body force is V bar d. Let us first consider with respect to deformed. So, I am just considering omega, that is deformed, and we are considering a subdomain here. considering a subdomain, and then the other force, or what is the other force? The traction vector, right? So traction vector of surface is the t bar, and del maybe omega, del omega is the surface. This is the traction. So traction is occurring along the surface, right? But body force along the body, and this is along the, okay. So now let us enforce equilibrium in terms of deformed configuration. So in omega, for in this omega, in the subdomain omega, okay. So what this will be? What this will be? This will be okay. So omega, and then minus rho, your double dot, d small b, plus b bar d small v, right? Right. This is plus integration del omega, t bar, d omega is equal to 0. Am I right? This, so this is over the surface, because this is traction vector, right? And this is the body forces, right? Fine. So now what we are going to do now is we are going to simplify it. So the first term, let us write it down. So omega traction vector, in the traction vector is always in the deformed configuration. We have to go back to the undeformed configuration. So traction vector can be expressed as what? First Pavlov-Kirchhoff stress tension in bar dA. Can I write like that? Right? In bar d, or if you would like to write, d omega is fine. Right? This one, and then plus this other, or it's fine, you just write it minus rho u bar double dot, plus acha. This I am going to, this because I have already changed with respect to undeformed configuration, right? This is with respect to undeformed I have changed. I am also going to change this in the undeformed. So how it will change? You see, acceleration it does not really care with respect to deformed and acceleration. So acceleration I can write just like that. But rho dV, what was the conservation law? If you can recall the conservation law, conservation law, if you can recall, I mean, I was just saying that, integration, omega 0, rho 0 d capital B is integration omega rho d small v, okay, or here you can see that rho 0 dv is equal to rho dv if you just consider unit area, and then here we do not know, but later you will see that can be converted, I mean rho 0 can be expressed in terms of rho, okay, later I will show it, so basically it you will see that J will be rho by rho 0. So basically rho 0 J is rho, or J is the this I will explain later, Jacobian of the deformation gradient. J will be the in the determinant of the those things I will show, okay. And then similarly, you will see the B0 d capital V will be small b small dv, okay, you see that. So what I am trying to do is that here I will just write it, you double dot, okay, and then this minus, instead of rho dv I am going to write rho 0 capital D capital V, and then B I am, because with respect to undeformed I am doing, I will write B0, D capital B. You see, they understand that 0, okay. So here everything the equilibrium was I was enforcing with respect to deformed configuration, but I am going to because I am writing down, trying to write down the equilibrium equation in terms of first Pavlov-Kirchhoff stress tensor, first Pavlov-Kirchhoff, I have to convert it back in terms of undeformed, because first Pavlov-Kirchhoff stress tensor is concerning with respect to the undeformed configuration. That is what I am doing all these things, you understand that, okay. So now here I can do so I will just write it in initial form I j maybe nj, d omega 0 plus omega, minus rho u double dot I, okay, plus b, rho 0, b 0, b 0, b 0, b 0 I, b 0 I, into d capital B is equal to 0. And here you see that now we can just convert this one into in this volume integral, right. This is a using Gauss theorem, this is a surface integral, we will convert into volume integral. So, it will be del p I j, and then because it is n j, unit normal vector. So, the gradient of this will respect to n j. So, that means it is del x j, you see that del omega 0 plus integration omega minus rho 0 u double dot I plus b 0 I dv is equal to 0. And so, if we combine everything, we are going to get omega 0, del p I j del x j, minus, plus b 0 I minus rho 0 u double dot I dv is equal to 0. So, I will take from there and I will come back here, please see that, and then I will come back here. What you see that this since omega 0 is an arbitrary subdomain, right, arbitrary subdomain, right, subdomain of omega 0, right. So, the integrand can vary. So, the integration, when we are writing, we have discussed it, right, in terms of weak form, strong form, right, all these things, when in terms of even finite element context I just discussed, right. Please note that, sorry, this will be capital X j, please note that capital X j, because it is with respect to undeformed, capital N is the undeformed, okay, please note that. So, p I j x j plus b 0 I minus rho 0 y double dot dv on d omega is 0. So, this is weak form, and for each and every point it is del p I j del x j, plus 0 I is equal to rho 0 u double dot I. So, that was the equilibrium equation which is enforced on each and every point, right. So, Piola-Kirchhoff stress tensor, essentially the form is same, x j comma j plus b 0 I is equal to rho 0 u double dot I, okay. Or if you would like to write down in terms of this is indicial notation, in terms of vector notation, in tensor notation, the vector notation. So, then you see this is divergence of p, okay, this is divergence, but then divergence with respect to undeformed configuration x j. So, it will be delta 0, okay, p plus b 0 is equal to rho 0 u double dot. You understand, this is the linear momentum balance. Please try to understand that, once again the internal forces are obtained by divergence of the first Piola-Kirchhoff stress tensor, but then the divergence must be taken with respect to undeformed configuration, that is why it is delta with respect to 0. If this is undeformed, it is unlike the Cauchy stress tensor. In Cauchy stress tensor, where we are trying to enforce the equilibrium, that was gradient with respect to deformed configuration. So, 0 was absent there, you see here all this. Okay, so, this is the in the form it looks similar to the Cauchy the equilibrium equation or linear momentum balance equation in of Cauchy stress tensor. Only difference is that there here it is referring with respect to undeformed, there it was referring with respect to deformed, that was the difference. Okay. So, now from there we will do the angular momentum balance as well. So, we are going to do angular momentum balance now. Angular momentum balance, or for first Piola-Kirchhoff tensor. Okay. So, now the way we proceed similarly we will do. Okay. So, here was the coordinate system x, y, z, or you can write the capital X, capital Y, capital Z, okay. Here is the body, okay, and then body once again we are considering a subdomain of the body, maybe here. In the subdomain of the body, the forces that is acting is minus rho u0 double dot, right? Once again we consider the deformed configuration. So, minus rho u double dot, and then same forces, body forces will be B, this is B, and then the traction vector will be I am considering a small domain, okay. Okay. So, I will take the moment with respect to the origin. So, I will join this thing, okay, with respect to the origin. So, x bar, this is the, I am assuming that position vector, this point is x is denoted by x bar, this is point P, you understand that, P, and I am considering a very infinitely small domain here, okay. So, let us do the angular momentum balance on the subdomain, in the with respect to the deformed configuration, okay. This is in the deformed configuration, and then we will get it back, deformed configuration, get it back to non-deformed. So, now you just do that. So, integration, so b bar d omega, minus rho bar d double dot, omega x bar, this is okay. This is the with respect to the origin, right, and then this n bar cross the surface, okay. Surface that I am training, this is volume, okay. This is volume and this is surface. You understand, S is the surface, P for volume, S for surface. So, differential of surface and the differential of volume, okay. Okay. So, now I will convert it in terms of what? I will convert it in terms of, I will just write it here, if it's come here. So, what I am going to do, this part I am going to first simplify this part. This part is simple. So, I am just going to simplify this part. So, the first, so second part, okay, and the second part, second part I am going to simplify. So, this one, what I am doing, I will write to do d bar d is 0. This one is, I mean not 0. This one, I am simplifying this expression. This is nothing but I will convert everything into with respect to the undeformed, okay, with respect to undeformed. So, x bar is this, and I am writing in indicial notation, right. So, cross product, right, t bar I will write in respect to p, okay, just wait, later I will write indicial notation. So, x bar t vector is what? Traction vector in respect to undeformed configuration, it will be p, and then it will be what? P n bar what? ds, right? You understand that? P tilde, okay? Can we write like that? Yeah, sure, right? Now I will everything write. This is xi ei cross, p will be p k l e k diode l, okay, and n1, n I am going to write maybe I j k l I k l j n j e j d s, okay. Please see that. Mind that here, you see that here, this is all this unit vector, these are with respect to what? Undeformed configuration. So, instead of using small e, I could have also used capital E as well, okay, because this is referring to undeformed configuration. Okay. So, if you would like to do that, you can do that, that is not a big deal, okay, that is not a problem. If you like to do that, or maybe let us write it small, no problem, but mind that these are all this base vector, okay. So, I will just simplify that, this one I am simplifying, I will do this, so E that this what is that, this is this is just dot what is this UAB. So, it will be I will just bring it here. So, I will remove this everything and I will retain this equation, because this equation is the main equation. I will because I will have to substitute now. So, from there maybe here I will do little simplification here. I hope that all of you can follow this. Okay, delta Lj. So, J I will just cancel out. Okay. So, NL I am writing NL and maybe epsilon J K IJK L M maybe. This is EI cross, no? This is EI, okay. So, EI. Now, we can convert this into volume integral, using Gauss divergence theorem. So, here you see this is with the NL is the unit normal. So, this will be with respect to capital X L, please note that, and this is the whole integrand x I K L epsilon m I k m ds. Am I right? This is perfectly fine. Huh? Okay. So, that is okay. Okay. For the second, so I will just substitute is that substitute here. So, I am just writing this equation. I will just write this equation here. Huh? So, this is I will. So, this part I have simplified there. So, this part I am just writing, and first part I know already. First part how I will write. So, maybe I will just first simplify the first person. So, this has been the second part. So, first part I am also simplifying. So, first part will be what? X bar b bar d omega minus rho, or I will use that this portion, because then I will substitute it there, so that it become very simple. First portion of this equation is nothing but what? X bar cross b bar omega minus rho u double dot dv. This is what? I am writing everything in terms of okay. I will just convert everything in terms of undeformed. Okay. So, b bar I will just write b bar 0, okay, b bar 0 please note that it is dv I am writing. So, it is b bar minus this thing, okay, please. So, b bar 0 minus rho bar u double dot d capital V. This was small v, this was small v, this was capital V. All these things we are expressing, this was small v, okay. But this is now capital V, because I have just converted. So, this I will just now I will write in indicial notation. So, this is will be maybe xi ei cross this is b0 e maybe I will write j minus rho 0 u b0 j e j e here dv, and then it goes on this xi. I will just take it out, b0 j minus rho 0 u j, okay, and then cross cross equals j dv, which is nothing but xi j minus rho 0 u j I j, maybe k I will write, but k epsilon k I j dv, okay. So, when I am writing xi j okay. So, now it's good. So, this is the second first expression, this is the second. So, now I am just simplifying this expression. I am just writing, please see that this, okay. So, the first term, this part is basically expressed like this. So, I am just writing, please see that xi b0 j minus xi rho 0 u j epsilon k I j dv. That is the first part, okay. And the second part is this one, del del xl, small xi p small kl epsilon m I k em ts is equal to 0, okay, clear. So, this equation become this. So, I am just removing this equation now, okay. So, now I will just simplify. What I will see that here, So, Kij, but here Mik. Okay. So, Kj I am going to replace Mk with Kj. Okay. So, that is not a problem. Huh? So, because we want to use the same in index, right. So, I can see that Kij I is fine, but here M should be replaced by K should be replaced by M and J should be replaced by K. So, that is what I will just do here. Huh? So, xi b 0 M I will write minus xi rho 0 u k epsilon k should be replaced by M I, J should be replaced by K M dV. Okay, clear? So, then basically we can del capital XL xi pkl epsilon M I k by M ds is equal to 0. So, here what we will do now, we will do one more simplification, that is we will do the differentiation of this. This differentiation, let us do that. Del small xi del capital XL pkl plus xi del pkl del XL, right. So, Mik ds is equal to 0, right. Because I am just doing this differentiation of that product, right. Then I will just simplify, keep on simplifying this. So, if I see that this part xi and this part this part I can put together, right, because this is xi b0 m minus xi rho 0 uk epsilon I k m dm, and this is also xi something. So, I can just combine these two, so that omega. So, I can combine this xi in b0 m minus rho 0 uk. Okay, uk, of course, here it is double dot, uk should be double dot, right, because it is acceleration. Please mind that acceleration. I am forgetting this acceleration, mind that acceleration. Okay. And I will just xi I have taken out. So, I will pkl by del xl, and then Mik em will be there, epsilon Mik em will be there. Okay. So, this is small dv plus integration. I will just remaining is this term, this term, this is del small xi del capital XL capital P K L epsilon Mik em d d. Here you mind that we have already converted it into volume integral, right. So, this is a volume, sorry for that, please note that we have already converted to volume integral, so it will be dv to be 0. Okay. Now, you please see what is this term. This term is what? This is nothing but linear momentum balance for first Piola-Kirchhoff, because if you can recall, this is nothing but linear momentum balance of first Piola-Kirchhoff, and this must vanish. So, it must vanish. So, this will be 0, right. So, only term that is remaining. So, this equation is is simplified to right here. So, and from there what we can see, this is the angular momentum balance equation, and from there what we can see that this is for arbitrary volume a subdomain, this is for arbitrary subdomain, arbitrary subdomain, right. So, this integrand must vanish. So, the integrand must vanish, right. So, the integrand must vanish. If the integrand must vanish, that we can rightly say that epsilon m I k, epsilon m I k del x I del capital X L P K L E m bar must be 0. What does it mean? What does it mean? This one, what does it mean? This mean that this product must be symmetric, because you see that L is a repeated index, right. L is a repeated index. So, when if you carry out this product, so this will be, this is a tensor of, so that this tensor, this itself, this product is a tensor, this product is a tensor, right. Why it is tensor? Because it is a, this is a tensor of rank 2, this is also a tensor of rank 2. So, when you take product and L is a repeated index, so when you take the product, it will be what? I am assuming that this is some tensor which will have two free index I and k, because there this is a dummy index, S will be dropped, and this is associated with epsilon m I k and E m. So, you know that we have derived that if this is equal to 0, then the tensor must be, if we expand, then you will see that it must be a product of a symmetric tensor. So, this basically expression is what? This expression is nothing but E bar transpose, E m transpose bar then del x x I x I by del x L P K L dot E E m is equal to 0. This is nothing but this, if you can recall from our initial notation. So, E m transpose E m cross del I del x k P K L E m, okay, E m is equal to 0. That is, and this condition, when this is, if there is a tensor in which there are two free index I L and m I k and E m, then m is a basically it's a different index, but I k, you see I k, then it must be a, see everything is a free repeated index here. Mind that this product is a tensor along the tensor, along with the tensor, you see m in the unit vector and I k is also there, you see. So, then you can see, if you expand, that this product itself will be a symmetric tensor, right. So, now come back here. So, then we see here. So, ultimately what derivation little involved, but then ultimate the ultimate relationship is very simple, right. So, what we see that from there, so since epsilon m I k so this must be symmetric, right, must be symmetric tensor, this product. So, what we can see? So, you can see that del x I capital X L P K L. So, you see this is a repeated index L. So, I j we can shift for symmetric. So, I j we can shift. So, del x k del capital X L P I L. This is this relationship. Please see that this relationship, or and this is that this quantity I am yet to define. This I will define later, del x I del capital XL, it is basically the derivative of a line segment of a vector segment vector in the deformed configuration with respect to undeformed configuration. This is called deformation gradient FIL. Okay. This is nothing but this is a tensor of rank 2 IL. This is called deformation gradient. Okay. Deformation gradient tensor, and it is extremely important in kinematics of deformation gradient tensor. Gradient. This is a tensor. This is a tensor of rank 2. So, if I just write in terms of instead of indicial notation, if I write in terms of tensile notation, so this is a tensor F tensor and this is P tensor. So, I can see F bar P bar transpose. So, what we see that Piola-Kirchhoff stress tensor is not symmetric, rather the product of this with respect to deformation gradient is symmetric. So, let us write. So, first Piola-Kirchhoff stress tensor is not symmetric, but its product with the deformation gradient with the deformation gradient is symmetric, Do you see that F bar P, F P, this is the product. And product is a second order tensor. So, when we write P and when we write P F, so what am I writing in terms of indicial notation, right. So, how we write del xi del capital Xj, and then P I am writing is the as what P Ij K J, right, or Jk maybe, right. You see the J is a repeated index and IP. So, this is nothing but this product, this is another tensor, say some tensor, say with some tensor of I comma I comma k or whatever, or I comma k whatever. You see that F bar P bar is symmetric. So, it is not symmetric tensor. So, P this we should write P 11, P 12, P 13 and P 21 is different, P 22, P 23, P 31, P 32, P 33. So, sigma bar is a symmetric. So, stress tensor. So, this is unlike Cauchy stress tensor. So, unlike Cauchy stress tensor, which was symmetric, right. In sigma is equal to sigma transpose, but P is not is equal to P transpose. Nevertheless, P into F, P F V, F into P is basically P transpose, F transpose. Okay, sorry. This is symmetric, okay. Okay, good. So, we have learned the linear momentum balance and angular momentum balance for first Piola-Kirchhoff stress tensor, and we have already learned it for Cauchy stress tensor. I will introduce another stress tensor in tomorrow's class. Thank you.